Hi, this is the first session of the topic graphs. Okay, before I go with the first topic, let me explain what is meant by a graph. Okay, you are aware that data structures are of two types. One is linear data structure, the other one is non-linear data structure. Okay, in non-linear data structure, the data is arranged in levels. So, in case of graph, okay, I can say that a graph is a non-linear data structure, okay, and it is made up of known number of nodes or vertices, okay, and there are edges that connect them. You might be thinking, where do we actually use this application in real world? We do use this, okay. Some of the applications like this telephone networks, okay, if I want to talk to another person who is in another part of the world, how do I connect? Okay, so we make use of this data structure called as graphs. Not only telephone networks, we also can make use of graph for the circuit networks and also social media networks. Okay, so if I want to connect the different parts, okay, in a circuit or in a real world, if I want to make any connections, I can make use of this data structure called as graph in order to code them. The first thing that we have is the vertex. Graph terminologies in that first one is called as vertex. You have also learned, this is the first one. So we have in trees something called as node. Node is like this data containing part. So here also vertex means it is something called as a synonym for a node itself. So as you can see in the example, there are three nodes, 1, 2 and 3. So data part is stored in something called as vertex. Now if I have the vertex, then I need something to connect these vertices. In order to form the network, I need to have this kind of lines. So the lines are represented by a term called as edge. As you can see here, there is edge. Okay. So what is a vertex? It is a synonym for a node. And what is an edge? Edge is a line that is joining these vertices. Okay. Next is, in edge itself, there are some other topics that we need to go through. That is, one is the undirected edge, and the other one, sorry, the other one is directed edge. Undirected edge, as you can see, it is connecting the two vertices, but the line does not have any direction to it. So that is called as undirected edge. So when you are trying to connect them, okay, the data can flow from 1 to 2 or else from 2 to 1. So this type of edge which is not having any direction to it, that is called as an undirected edge. So if you have an undirected edge, this is how you represent it. Remember, put the simple bracket and put the vertices. Okay. Likewise, we have directed edge also. Directed edge means an edge which is having a direction to. So here as you can see, okay, the control is flowing from 1 to 2. So you have to show it in the angular bracket. In the other case, it was simple bracket in case of undirected edge, whereas in this case, it is an angular bracket that you have to use in order to represent them. Okay. So what is a vertex if you ask? Vertex means the nodes where the data is stored. What is meant by the edges? The connecting part of the two vertices. That is called as an edge. And that also, if there is no direction that is shown, that is called as undirected edge. And if there is a direction shown, then it is called as a directed edge. Okay. So I hope it is clear. We'll go to the next one. That is the definition of the graph itself. This is very, very important. You have to learn the definition of the graph. Here it is, definition of the graph. Let me read it for you. A graph G, I am denoting it using the letter called as capital G, is defined as a pair of two sets. It is defined as a pair of two sets, V and E. Okay, and a graph is denoted with this particular representation. G is equal to V comma E. V is the vertices and E is for the number of edges. Okay, so graph can be defined using two sets. One is the set of vertices, the other one is the set of edges. So if you look at this particular graph here, okay, So this, as you can see, it has direction, so I can call this as a directed graph. Okay, I need to represent its vertices, so here I have given the vertices. So I have written the vertices in a flower bracket. So 1, 2, 3, 4, 5, 6. As you can see, 1, 2, 3, 4, 5 and 6. Likewise the edges also. Because this is having direction, I have written the edges using the angular bracket. So one edge is from 1 to 6, then one is from 6 to 4, then 4 to 3, 5 to 3, 5 to 6, 1 to 2, 2 to 3. Okay, so this is how we write. And we can also show the number of edges here. Please see here. See, the number of vertices are 6 and the number of edges is 7. So if they ask you how to define the graph, you will say that it is a data structure which is denoted with the capital G, and it is made up of two sets of data. One is the number of vertices denoted by capital V, and the other one is the number of edges which is denoted by capital E. Okay, and you show the number of vertices for an example graph. Likewise, in graph also we have directed graph. If there is directed graph, we also will have undirected graph. See here, let me define a directed graph. A directed graph G is equal to V comma E, in which every edge is directed, is called as a directed graph, also called as digraph. Directed graph is also called as digraph. Remember this. So here in this example, we have the directed graph. Likewise, undirected graph. There is a graph in which the edges do not have any direction to it. So this type of graphs are called as undirected graph. Okay, as you can see, there are some examples that are given. Some more topics are there that needs to be covered. Self-loop. That means an edge. Okay, there is an edge which will connect to the same node. So here there is an edge that is connecting from 1 to 1 itself. So that is called as a self loop or a self edge. The definition is, it is an edge which starts and ends on the same vertex. Likewise, we have complete graph. See, complete graph. Okay, we know what is a graph. Now we'll look at what is a complete graph. Let me define it for you. A graph that is having the two sets G is equal to V comma E is said to be a complete graph if there exists an edge between every pair of vertices. That means every vertex, okay, has to be connected using an edge. So such graphs are called as complete graphs. As you can see, one is connected to 2 also, one is connected to 3 also, one is connected to 4. So one is connected to all the other vertices in the graph. Likewise, even others also. 4, for example, 4 is connected to 2, 4 is connected to 1 and 4 is connected to 3. So this type of graphs are called as complete graphs. Okay. Next one is path. Okay. Path means, let me define it for you. Okay. A path is denoted using the sequence of vertices, and there exists an edge from one vertex to the next vertex. That means we are showing the way through which the control is flowing. So we can go from 1 to 2, then 2 to 3, then 3 to 4, and that is what. Okay, so the data is flowing from 1 to 2, 2 to 3, 3 to 4. This is shown using the path. Likewise here. Okay, here also this is a directed graph. So 1 to 2, 2 to 3, 3 to 4. And I have specially used this angular bracket because it is a directed graph. Likewise, simple path. A simple path is the one in which all the vertices except possibly the first and last are distinct. Okay, first and last are distinct. The others can be repeated. So I can start at 1 and 2, then I can go 2 to 3, then 3 to 4. Since this 1 and 2 and 3 and 4 can be unique, others can be repeated. Okay, length of the path. Length means how many edges are there. Okay, so that is what. Next one, connected graph and disconnected graph. Okay, so let me define it for you. A connected graph is said to be a connected one if and only if there exists a path between every pair of vertices. See, that means every vertex has to connect to other vertex in the graph. That is called as connected one. Disconnected means there might be an edge, okay, that there might be a vertex that is not connected to other vertex. As you can see in this example here, all are connected. See, 1 to 2, 2 to 3, 3 to 4 connected. But what about this vertex 5? Vertex 5 is completely disconnected from this particular graph. It is a part of the graph, but one part of the graph has no connection to the other part. So such type of graphs are called as disconnected graph. I hope you are understanding. So this is how we write the definitions. Okay. So we have a lot of terminologies that you need to remember. Next part is the representation of the graph. Very, very important. Okay. Let's discuss this topic. Graph representation is done using two methods. One is your adjacency matrix method and adjacency linked list. Okay. So we will look at the two methods. One is using the adjacency matrix. This particular definition is very, very important. Let me read it out. Let G is equal to B, E be a graph. Let N be the number of vertices in the graph. Remember, N be the number of vertices. The adjacency matrix A is defined as follows. So for a given matrix, okay, so we are using 2D matrix here. So there will be two parameters, two indexes I and J. So it can have two values. The matrix can have two values. One is 1, the other one is 0. When to have 1? If there exists an edge between the vertex I and J. When we are trying to write the matrix, if there is a vertex that exists between if there exists an edge between two vertices, then that particular value will become 1. Otherwise, it is going to be value 0. So 0 if there is no edge from the vertex I to J. Okay. So let me take an example and explain this to you. See here, we have taken an example of directed graph and undirected graph. Now you know what is directed graph and undirected graph. Let's try to do the adjacency matrix for this. See here, okay. This is the adjacency matrix representation. So 2D matrix. So whatever vertices you have, that will become the index. So 0, 1, 2, 3. Likewise here also 0, 1, 2, 3. If I had A, B, C and D, this would be A, B, C and D. Here also it would be A, B, C and D. Okay. Now, you have to see if there is an edge between those vertices 0 and 0. In first case, it is between 0 and 0. Okay. So, see, is there any edge between 0 and 0? There is no edge between 0 and 0. So, the adjacency matrix will have the value 0. Likewise, next one is 0, 1. 0, 1. Let me use a different color. Okay, 0, 1. So, check. Is there any edge between 0, 1? Yes, there is. So, this will become 1. Let me take one more. Let me take this one. Okay. So, the row value is 3. Column value is also 3. So, check. Is there any edge between 3 and 3? Here, no. So, it is having the value 0. Likewise, check. Let me take this one. This one. Okay. So, it is having the row value 2. Column value is 1. So, 2 and 1. So, check if there is an edge between 2 and 1. 2 and 1. There is an edge, but because it is a directed edge, the control is from 0 to 2 and not from 2 to 0. So, we can't say that there is an edge. So, I have given the value 0. Okay, this is how we write the adjacency matrix for a directed graph. Now we'll look at the undirected graph. See here, undirected graph. Okay, undirected means there is no direction. So from 0 to 1 also we can say, and from 1 to 0. It goes in the opposite directions. So if I take the example here, okay, you know it is a 2D matrix. So 2D matrix, okay. So here, so let me take this one, 2 and 0, 2 and 0, okay. So is there any edge between 2 and 0? There is an edge between 2 and 0. So this value becomes 1. Okay. Let me take 2 to 3. So there is an edge between 2 to 3. So the value should become 1. So 2 and 3. See its intersection here. It is having the value 1. 2 to 3 means 3 to 2 is also valid because it's an undirected graph. So check 3 and 2. So yes, it is having the value 1. This is the adjacency matrix representation for the graph. Similarly, linked list representation. Okay, this is fairly simple. You know by now what is meant by the linked list. So in that also there are different types. Here we will be using the singly linked list in order to represent the graph. Okay, so let me read it out. In the adjacency linked list, okay, an adjacency linked list is an array of n linked lists where n is the number of vertices in the graph. See here, this is the graph. Okay, this is the graph. You have to write the vertices in the form of a table like this. So each row will be having its edge, this vertices name. So 0, 1, 2 and 3. Now if there is an edge between 0 and any one of them, you show it in the form of a node of the linked list. So here if you see, from 0 there is 0 to 1. So I have represented this 0 to 1. Then you check, is there any other edge between 0 and any other vertex? So 0 to 3 is also possible. So here it is. Is there any other one? Yes, 0 to 2. So that is also shown. Okay. Similarly, for the other vertex. So 2. From 2, can you check if there is any vertex that is going from 2 edge? So 2 to 3 is there. So 2 to 3. So from 2 to 3. Okay, because this is the last node. So I am showing the address part as null. Okay, so I hope you are understanding. Similarly here, adjacency linked list. This is the undirected graph. So from 0 to 1 there is, and 0 to 2. So from 0 there is to 1 and there is also to 2. Let's check for any other value. Okay, I am not showing for all of them because I think it is, you are able to understand. Let me take the example of 3. So 3. From 3 we have a edge that is going to 1, and from there we have one edge going to 2. Okay, so from 3 we have an edge for 1 and there is an edge for 2. I hope you are understanding. This is how we do the representation of the graph. But which do you think is the best? It comes with the explanation here. Let me read it out. Which graph representation is the best? Is the linked list representation better or is the matrix representation better? So it depends upon the following factors. One is the nature of the problem, algorithm, type of input and number of vertices and edges. See here, in number of vertices and edges also we have two conditions. Let me show it to you. If the graph is sparse means the lot of values in that particular matrix is having 0 values. So that time we can make use of adjacency matrix. Otherwise, if the graph is dense, that means if there is a lot of edges between the graphs, between the vertices in the graph, then we can make use of sorry, okay, the first one we can make use of when there is sparse matrix, because sparse matrix means lot of non-zero values, okay, not of zero values, sorry. In that case, what we can do is we can simply represent that by making use of a linked list. And when the graph is dense, we can simply make use of the adjacency matrix. Okay, so you can use any of the representation for showing the graph, but if the graph is dense, then you make use of linked list, or if your graph is fairly simple, having a lot of if it is dense, make use of adjacency matrix, otherwise make use of the linked list representation. In this itself, we have something called as a weighted graph. We know what is a graph. Now we will look at what is meant by weighted graph. See here. Okay. So there is vertices, there is edges. Now edges have an extra information to it. That is called as weighted. See the definition. A graph in which a number is assigned to each edge in the graph is called as a weighted edge. Okay. What this weight can be referred to as? It can be referred to as a length and capacity. So it will be some value that is attached to it. Okay. Again, we will represent this particular graph in the form of linked list and also using the adjacency matrix. Okay. See here, for the adjacency matrix, okay, if there is an edge between I to j, then we write the weight in the linked list. Previously, we used to write 0 and 1 in the adjacency matrix. Now we will represent the weight if there is an edge. Otherwise, it will be infinity if there is no edge between I to j, for example. See here. Okay. So this is the graph. This is a directed graph. Okay. So I have written 0, 1, 2 and 3. Likewise, even the column. So 0, 1, 2 and 3. If there is an edge between, so 0 and 0. See, remember, if it is the self node or a self loop, okay, we are trying to refer to a self loop, then give the value as 0. So from 3 to 3, so from 3 to 3, the value is 0. See, from 2 to 2, the value is 0, like this. Okay. If not, then you represent using the weights or you give infinity. See, there is an edge between 0 to 1. So, there is an edge between 0 to 1. So, what is the weight? Its weight is 10. Let's see one more. Okay, let me see one more. See, 2 to 3. 2 to 3. So, here. 2 to 3. So, 2 to 3. 2 to 3, weight is 30. Correct. What about 3 to 2? 3 to 2. 3 to 2, there is no edge. So, 3 to 2 is having the value infinity. Are you understanding? If there is an edge existing, give its weight. If not, give the value infinity. And if it is trying to check whether there is a node, whether there is a vertex, whether there is an edge between the same vertex, okay, then you give the value 0. This is how we represent using the adjacency matrix. Okay, let me erase this first. Okay. Now the linked list. See, we have written the rows 0, 1, 2, 3. Now this is the matrix name. Okay, so not the matrix. This is a representation because I am giving the graph name as A. Okay. So what we do is we check whether there is an edge between the given node and the next one. And if it exists, we write its name along with its weight. So here if you see, from 3 to 1 there is edge, 3 to 1, and its weight is 25. So from 3, there is an edge called as 1, which is having the weight as 25. So we write it as 1, 25. Are you understanding? I hope you are understanding. So next one. Okay, so here it is. From 0 to 1 we have, so 0 to 1 we have the weight as 10. So 0 to 1 we have the weight as 10. Okay, what about 0 to 3? 0 to 3, check the graph. Is there any edge between 0 to 3? There exists no edge. So here 0 to 3 is having the value infinite. Okay, likewise the linked list representation. One, you give the edge name, the vertex name along with its weight. Okay, there is a small algorithm here, because this is a function to read the adjacency matrix and adjacency linked list. Okay, so for the matrix, so it's a 2D matrix, so 2 indexes, then there is, based on the number of values you want, there would be a integer called as n. So I equal to 0, I less than n, I plus plus, j equal to 0, j less than n, j plus plus. Input the values into the matrix. So a of I comma j. Similarly for the list. See here. Okay, list. Okay, so there is only one column, right? So there is I equal to 0, I less than n, I plus plus. We only ask the user, okay, how many nodes are adjacent. Based on that only we will try to form the linked list. So if it is 0, then we don't have to create anything. Otherwise, if there is an edge between, if you have given that there is an edge, that is node that is adjacent, then we try to put the item and we will try to insert it into the linked list. We insert it. Okay, so this is how the topics of graph goes. This is the first part. So I'll take an example and let me show you, by solving a problem. So here there is a graph, and this is the adjacency matrix representation and adjacency link representation. So you are supposed to draw the lines like this between the representation, because like this. Okay, try to draw it. I have not drawn this because it would look dirty here, because the lines are also not so straight. But when you write for the exam, you refer to the notes and you try to draw the lines. Okay, now we have to show whether this is what type of graph. First of all, the first figure, what is the type of graph here? The type of graph here is undirected graph, correct? So the connection is there from A to D as well as from D to A. Remember this. Now I'll try to fill the adjacency matrix. Okay, so A to A, first one is A to A. Okay, so A to A, check if there is an edge between A to A. There is no edge. You simply give the value 0. Okay, A to B, next one is A to B. Check if there is an edge between A to B. Yes, there exists an edge, so give the value 1. A to C, check if there is an edge between A to C. No, so give the value 0. Likewise, A to D, check if there is an edge between A to D. Yes, there is, so I'll give the value 0. A to E, check if there is an edge between A to E. No, 0. A to F, it should be a direct edges, that's what. So A to F also no, like this, 0. This is how you can go on filling the entire matrix. B to A, B to A, so here it is, B to A, so 1. B to B, 0. B to C, no edge, so 0. B to D, no. B to E, no. B to F, B to F, 1. C to A, C to A, 0. C to B, 0. C to C, 0. C to D, C to D, 0. C to E, 0. C to F, 1. Like this, you go on filling the entire matrix. Linked list representation. What we do is, we it's like a 1D array. So for each edge there would be each vertex there would be one row. So we have 6 of them. So 1, 2, 3, 4, 5 and 6. So A, B, C, D, E and F. So we'll check the possible connections. From A we have 1 to B and the other one is to D. So one we have for B, so that will become one node like this, B. From there is one more, D. That is the last one. So give its data address part as null. Likewise, let's do for F. Okay. So F is connected to B, F is connected to E, and F is also connected to C. So from F we have 1 to B. There is no order. Order is up to you. Whichever you want, you write first. So from B we have one more. We have a C. From C we have one more. That is E. Like this. Are you understanding? This is how we represent. Okay. Similarly, if it is a directed graph, we can do the same. We have to write the those values. The indexes, sorry. Okay. Now the idea is, for example, if I take the vertex A and D, the edges from A to D. So from A to D. So A to D will get the value 1, whereas D to A D to A gets the value 0. Are you understanding? This is how we do the adjacency matrix. Likewise for the linked list also. 1, 2, 3, 4, 5, 6. A, B, C, D, E and F. Okay, so from A we have D. Look at the graph from A to D and A to C. So there is no order, so I will first write D and then I will write C. Next, let's do for B. So B is having only one vertex that is going from B, that is B to E. So from B we have only one, that is E. This is how we do the representation. Likewise, you can do for all the other values. Okay. So I hope you have understood. In this session, we have seen some of the graph terminologies. We have defined the graph. We have seen how to represent the graph in the form of a matrix and also in the form of linked list. Also, we have seen another type of graph that is called as weighted graph, and we have also seen its link representation and also its matrix representation. Okay, I hope you have understood the session. Go through the notes, and if there is any doubts, please contact me. Okay, we'll end up this session here. In the next session, we'll continue with some other topics related to graphs. Thank you so much.